Block 1. The Unseen Architect of Modern Physics. Hello, brilliant minds and history enthusiasts. Welcome to the channel. Today, we're pulling back the curtain on one of the most glaring and controversial chapters in the entire history of science. We're not just talking about a forgotten scientist or an overlooked discovery. We are diving deep into the story of an extraordinary physicist whose revolutionary work didn't just add to our knowledge, it fundamentally shattered a pillar of reality, a law of the universe that was considered as sacred and unbreakable as gravity itself. Her breakthrough was the key that unlocked a new era of physics. Yet, when the highest honor in science, the $1 million Nobel Prize, was awarded for this very discovery, her name was nowhere to be found. This isn't just a sad story about a missed award. It's a profound intellectual betrayal, a $1 million oversight that exposes the deep systemic biases that have shaped the very narrative of scientific achievement. So, what does it truly mean to overthrow a law of physics? Imagine for a moment the foundational principles that govern our world. Things fall down, not up. An action creates an equal and opposite reaction. These aren't just theories, they are the bedrock of our understanding. For decades, one such pillar was the law of conservation of parity. In simple terms, this law stated that the universe was ambidextrous. It had no inherent left-handed or right-handed preference. If you watched a physical process, say a particle decaying, and then watched its perfect mirror image, the laws of physics should be identical in both scenarios. The mirror world should behave exactly like our own. This principle of symmetry was elegant, it was beautiful, and it was considered an absolute truth, woven into the very fabric of quantum mechanics. To question it was like questioning mathematics itself. It was scientific heresy. Yet, in the mid-1950s, a crisis was brewing in the field of particle physics. Two brilliant theoretical physicists, Cheng-Dao Li and Chen-Ning Yang, were grappling with a puzzle involving particles called K-mesons. These particles seemed to decay in ways that violated existing rules. But the only way to explain their behavior was to propose something unthinkable, that in the realm of the weak nuclear force, the force governing radioactive decay, the law of parity might not apply. It was a radical, almost absurd idea. They had the theory, a mathematical suspicion, but they had no proof. Theories in physics, no matter how elegant, are worthless without experimental validation. They needed a genius, an experimentalist with unparalleled skill and courage, to venture into this unknown territory and conduct an experiment that most physicists believed was a waste of time. They needed someone who could ask the universe a direct question: are you truly symmetrical? This is where our unseen architect enters the story, Dr. Chen-Sheng Wu. A titan in the field of experimental physics, she was widely regarded as the world's foremost expert on beta decay, the very process governed by the weak force. While others dismissed the theory from Li and Yang as too far-fetched, Wu understood its profound implications. She saw the possibility, the crack in the foundation of physics, and she knew she was uniquely qualified to test it. She possessed a rare combination of intellectual rigor, technical mastery, and an unwavering commitment to empirical truth. In a field completely dominated by men, where women were often relegated to supporting roles as calculators, Wu was a force of nature, a leader whose expertise was undeniable. It was this reputation that led Li and Yang to her door. They had the revolutionary question. She was the only person on Earth who could get the answer. The stage was set for a discovery that would change everything. But it was also the prelude to a shocking injustice that would see her male colleagues receive the ultimate prize for the monumental truth Wu single-handedly uncovered. Block 2. The experiment that broke physics. With the audacious theory from Li and Yang in hand, Chen-Sheng Wu knew that proving it would require an experiment of unprecedented difficulty and precision. This wasn't something that could be slapped together in an afternoon. It demanded pushing the boundaries of technology and scientific methodology. The core idea was to observe the beta decay of a radioactive element under meticulously controlled conditions. If the law of parity held true, the electrons emitted during the decay should fly off in random directions, showing no spatial preference. But if parity was violated, there would be a detectable asymmetry. More electrons would be emitted in one direction relative to the nucleus's spin than in the other. To see this effect, Wu needed to align the spins of the atomic nuclei, essentially making them all point in the same direction like tiny spinning tops. And there was only one way to do that, by subjecting them to a powerful magnetic field at an incredibly low temperature. We're not talking about a cold winter day. Wu needed to cool her radioactive sample of cobalt-60 to just a fraction of a degree above absolute zero, the theoretical point where all atomic motion ceases. This is a temperature of around -273.15 degrees Celsius, a cold so profound it's barely achievable on Earth. At this temperature, the chaotic thermal jiggling of the atoms would stop, allowing the magnetic field to lock their spins in place. This was a monumental technical challenge. She needed the expertise of the low-temperature physics group at the National Bureau of Standards, and she had to persuade them to dedicate their highly specialized equipment to her heretical experiment. Recognizing the earth-shattering potential of the discovery, she famously canceled a long-planned trip to the Far East with her husband, choosing to stay and work through the Christmas holidays of 1956. The pursuit of truth could not wait. The experiment was a masterpiece of design. The team suspended a crystal of cobalt-60 in a complex cryostat, a high-tech refrigerator, and slowly brought the temperature down over days. As the atoms aligned, Wu and her team held their breath and began to measure the direction of the emitted electrons. The initial data began to trickle in. At first, it was inconclusive. But as the system stabilized and the measurements became clearer, an astonishing picture emerged. The electron counter placed at one pole of the cobalt nucleus was clicking far more rapidly than the counter at the other. The electrons were not flying off randomly. They were preferentially being emitted in a specific direction. The universe at the subatomic level was playing favorites. It had a preferred direction. It was, in a sense, left-handed. The mirror image was the same. The moment she saw the definitive asymmetrical data on her instruments, Wu knew. She had done it. Parity was not conserved. A fundamental law of physics accepted for over 30 years had been shattered on her laboratory bench. The result was so shocking, so contrary to all accepted wisdom, that Wu's team spent weeks rechecking every wire, every calculation, every piece of equipment, trying to find a mistake. There was none. The result was real. This was not just an incremental advance, it was a revolution. It was the experimental proof that opened the floodgates for what would eventually become the standard model of particle physics, our current best description of the fundamental forces and particles of the universe. Li and Yang's theory was brilliant, but it was Wu's experiment that transformed it from a speculative hypothesis into a concrete, undeniable fact of nature. She had provided the empirical evidence, the smoking gun, that forced the entire physics community to rewrite its textbooks. Her work was the linchpin, the critical and decisive act that validated the entire enterprise. It was, without exaggeration, one of the most important and elegant experiments of the 20th century, and it seemed destined for the highest possible recognition. Block 3. A Legacy in the Shadows. In the fall of 1957, less than a year after Chien-Shiung Wu's groundbreaking experiment, the phone call came from Stockholm. The Nobel Committee announced that the prize in physics was being awarded for the discovery of parity violation. The world of science celebrated a monumental breakthrough that had reshaped our understanding of the universe. But as the names of the laureates were read out, a shocking omission became clear. The prize was awarded to Tsung-Dao Li and Chen-Ning Yang, the theorists who had first proposed the idea. Qin Wu, the experimentalist who had conceived of, designed, and executed the sole definitive experiment that proved their theory correct, was left out completely. The glory, the history, and the $1 million prize went to the men. Her indispensable contribution was relegated to a footnote. The decision sent ripples of disbelief through parts of the physics community. Why was she excluded? The Nobel Committee has never publicly explained its reasoning, but several justifications have been speculated over the years. One argument is that the Nobel Prize has historically shown a bias towards rewarding theorists over the experimentalists who prove their work. Another is that her experiment, while crucial, was a confirmation rather than an initial discovery. But this argument falls flat, as numerous Nobels have been awarded for the experimental confirmation of theoretical ideas. The most unavoidable factor, however, was the pervasive, systemic gender bias of the era. In the 1950s, the idea of a woman being the principal architect of such a pivotal discovery was, for many in the establishment, simply unfathomable. She was the woman who did the work, but the men were the geniuses who had the idea. It was a narrative that fit neatly into the prejudices of the time, regardless of the scientific reality. The betrayal was not just from the committee. In their Nobel lectures, Li and Yang acknowledged Wu's work, but they did not use the platform to champion her as an equal partner in the discovery. The historical record was being written, and her role was being minimized in real time. Despite this monumental snub, Wu's career continued to be extraordinary. She became the first female president of the American Physical Society and received many other prestigious awards, including the inaugural Wolf Prize in Physics, often considered second only to the Nobel. But the injustice of 1957 lingered. She rarely spoke of it publicly, maintaining a dignified silence, but in private letters she expressed her pain, once writing, "I wonder whether my name will be forgotten." Her work, however, is impossible to forget. It is a cornerstone of the Standard Model of particle physics, the theory that describes almost all of modern physics. Every time a physicist studies the weak force, they are building upon the foundation that she laid. Her legacy is written not on a Nobel medal, but in the very equations that describe our universe. She overthrew a law of physics, and in doing so, exposed the unwritten, biased laws of the scientific establishment. Her story is a powerful, infuriating, and ultimately inspiring reminder that genius and truth must often fight against the friction of convention and prejudice. It forced the scientific community to begin a long, slow conversation about credit, collaboration, and the invisible figures whose work makes breakthroughs possible. Do you think this injustice can ever be truly rectified? And how can we better honor the hidden figures of science today? Subscribe for more untold stories, and see you in the next one.